Welcome back. In the last lecture, so we have seen that the Schwarz space does not have an identity under convolution. So, however, we call that a family to be an approximate identity if it satisfies this 3 relation, just like before we have seen about the fair kernel, Poisson kernel in the series setup. But in the discrete we have an identity. So, we are lucky to have an identity, but in circle we did not have that kind of privilege. So, if now the question is that does there exist lot of approximate identity in the Schwarz space. So, let us construct let phi is in the Schwarz space. If let and phi is greater or equal to 0 with integral minus infinity to infinity phi of x dx, this is equal to 1. So, any non-zero function in the Schwarz space I can take and then I can whatever the function is, that if the integral is not equal to 1, I can divide it by the integral and then we can actually get this condition of. So, this is not very superficial, we can always get for any non-negative Schwarz class function. Now, for delta greater than 0, define phi delta of x to be equal to 1 over delta phi of x by delta. Okay. So, what do we know? So, my claim is that this family phi delta, delta greater than 0 is a good family. Okay, so the first condition of course is true, phi delta of x, this is greater or equal to 0 for all delta and for all x, because phi is greater or equal to 0 and delta is greater than 0. Secondly, integral minus infinity to infinity phi delta of x dx, this is nothing but by the change of variable minus infinity to infinity phi of x dx, and which we have assumed to be 1. Now, the only thing we need to check is the third property, and so for that okay. So, now let eta be positive and then we are writing mod x greater than eta phi delta x dx. So, this is equal to mod x greater than delta 1 over delta phi of x by delta dx. Now, if I make a change of variable, then I will get this is phi of y, then this is 1 over delta dx is dy. Now, if mod x is greater than eta, then mod y is going to be greater than eta by delta, because here I am substituting this. If mod x is greater than this, then mod y is greater than eta by delta. Okay, so, now phi is an integrable function being a Schwarz class function. Therefore, the tail of the integral is going to be small. So, this will definitely go to 0 as delta goes to 0, because whenever you are making the delta to be small, eta is a fixed number, eta by delta is going to blow up. So, therefore, this this satisfies all the three properties to be a good kernel. Example, you can take various, but you can always take that phi of x is equal to e to the power minus pi x square. This what we have done. So, this then phi delta of x, this is equal to 1 by delta e to the power minus pi x square by delta square. So, this family is going to give us a good kernel. Now, the question is that why it is an approximate identity, just like in the Fourier series case. So, this is the theorem, let k delta be a good kernel, let the family. Remember that this is always a family we are talking about, not in individual single function, be a good kernel if f is in Schwarz space, then good kernel in Schwarz space. If f is in Schwarz space, then f convolution of k delta of x converges to f of x uniformly as delta approaches to 0. Okay. So, the proof is exactly the similar kind of technique what we have adopted to prove in the circle case. So, now what we want to see is that f convolution of k delta of x minus of f of x, this is equal to integral minus infinity to infinity f of x minus of y k delta of y dy minus of f x. Now, this minus of f x in place of f x I can write this is minus infinity to infinity k delta of y dy. Therefore, mod of f convolution of k delta of x minus of f x, this is less or equal to integral minus infinity to infinity mod of x minus of y minus f x mod k delta of y, because we are taking k delta to be non-negative. So, this is there. Now, we know that f is in Schwarz space. So, in particular f is a continuous function. Now, on a compact set it is uniformly continuous. So, now what one can do is that as f is in Schwarz space, for epsilon greater than 0, there exists delta greater than 0 such that mod of f of x minus of y minus of f y f x is less than epsilon whenever mod of y is less than delta. So, now in that case what we do is that we will, so therefore, f convolution of k delta of x minus of f x is less or equal to mod y less than delta plus mod y greater or equal to delta this of mod of f of x minus y minus f x into k delta y dy. Okay. In the first integral, as you can see that f is uniformly continuous, it is in the Schwarz space. So, I can pull out the epsilon. So, this is less than epsilon into minus infinity to infinity k delta y dy, dominating it from minus delta to delta, it is always this the bigger, and now plus this I can pull out like the supremum over all x such that mod of f of x belongs to R. If I pull out, then this is mod y greater or equal to delta, sorry, there are two deltas. What I will say that this is eta mod y less than eta, then this is less than eta, this is greater or equal to eta. So, this is mod y greater than eta k delta y dy. So, because it is it is a good kernel. So, this part is going to go 0 as delta goes to 0. So, therefore, this entire thing is small, hence, and this is already a small number, f convolution of k delta converges to f uniformly, because there is no x dependency on the right hand side. So, this suggests that although we do not have an identity in the Schwarz space under convolution, but we have a family which is an approximate identity. So, that solves some of our problem what we will encounter. Okay. So, now our next target should be the Fourier inversion theorem. So, before that, let us make an observation. If both f and g they are in the Schwarz space, then integral minus infinity to infinity f of x g hat of x dx. Remember, if f is in the Schwarz space, f hat is also in the Schwarz space, and so this integral is well defined. So, minus infinity to infinity f hat at x g of x dx. Okay. So, this is very simple to prove, only what one needs to see the change of the order of the integration. And so, now if you start with the left hand side, so this is f of x integral minus infinity to infinity g of y e to the power minus 2 pi I y x dy dx. Now, because both f and g are in the Schwarz space, so what we know that f of x g of x modulus g of y dx dy, this is finite. So, therefore, we can make the change of the order of the integration minus infinity to infinity g of y, and then minus infinity to infinity f of x e to the power minus 2 pi I y x. Now, this integral is dx, this is dy, which is equal to minus infinity to infinity g of y f hat at y dy, and that is what is our required equality. This is sometimes is referred to as the multiplication formula. Okay, so now we are all set to state and prove inversion theorem, or rather we will call it Fourier inversion. If f of f belongs to the Schwarz space, then recall that in the Fourier series case we have, if f hat has certain decay, and then what one would say that f of x is equal to summation f hat of n e to the power 2 pi I n x if f is one periodic function. So, here in this case what we will get f of x, this is equal to minus infinity to infinity f hat at xi e to the power 2 pi I j x d j. No minus sign in the e to the power 2 pi I. Okay, so first let us check that enough to prove for x is equal to 0. That is f of 0, this is equal to minus infinity to infinity f hat of xi d xi. If we prove this for all functions in the Schwarz space, then we take any arbitrary function and define for a fixed, for x fixed, for each x define g of y, this is equal to f of x plus y, then g is in the Schwarz space. So, by the inversion, by the formula, if we are assuming that it is true, then g of 0, this is equal to integral minus infinity to infinity g hat xi d xi. Now, g of 0 is what? G of 0 is f of x. Now, g hat of xi, g is the translate of f. So, it is going to hit with the character. So, this is nothing but minus infinity to infinity f hat of xi e to the power 2 pi I j x d j. So, it is only we need to prove it at one point, that is at f at 0 is integral minus infinity to infinity f hat of xi d xi. Okay. So, now for delta greater than 0, define phi delta of x, this is equal to e to the power minus pi delta square x square. So, if we compute delta of xi, then this is going to be, what we have seen is that this is nothing but e to the power minus pi x square. So, this because if you take the Fourier transform of this, then this is equal to if I take the Fourier transform of phi delta of x, then we are going to get this. That is what we have seen earlier. And now we know that this is going to give us a good kernel, this family is going to give us a good kernel. So, therefore, what one can see that we know f convolution of phi delta hat, this converges to f uniformly as delta goes to 0. So, now this that means f convolution of phi delta hat at 0 converges to f of 0. From the above proposition, we know that integral minus infinity to infinity f of x phi delta hat at x dx, this is equal to minus infinity to infinity f hat of xi phi delta of xi d xi. This is what we know from the previous proposition. Phi delta hat of minus of x is equal to phi delta hat of x. So, because this is a radial function, even function. So, therefore, this is nothing but equal to f convolution of phi delta hat at 0. Now, this is equal to minus infinity to infinity f hat of xi e to the power minus pi delta square xi square d xi. Now, LHS, this converges to what? Because it is an approximate identity. So, this converges to f of 0, and this we can push the limit inside. So, this is going to this quantity as delta goes to 0, this quantity goes to 1. So, this is minus infinity to infinity f hat of xi d xi, and that is what is the proof for the inversion theorem. So, so that is one. So, in one of now once we have that as a corollary, we can get that if f is in the Schwarz space and f hat of xi, this is equal to 0 for all xi, then f is identically equal to 0, because of the inversion formula, that is true. So, this shows that the this shows the uniqueness of the Fourier transform. That means, that is, if f hat of xi is equal to g of hat of xi, where both f and g are in the Schwarz space for all xi, then f is identically equal to g. Okay. So, now let us see that we know, let us define f is the map from the Schwarz space to the Schwarz space by f acting on f is nothing but f hat. That means, the map f going to f hat. So, what we have seen is that descript f, the Fourier transform, is a 1-1 function. That is what we have seen. Now, the question is now very interesting one, if you look at f composition with f at f. Now, this is going to be f f of f hat. So, now f of f hat is going to be integral minus infinity to infinity f hat at xi, then e to the power minus 2 pi I xi x d xi. Now, this is nothing but f of minus of x. and now if you take it 3 times, if we are going to do that, then this is again what you are going to get the Fourier transform of this. So, this is nothing but minus of infinity to infinity, Fourier transform of f of minus x means f of x e to the power 2 pi I j x dx, which is equal to f hat of minus of xi. Now, if you take it 4 times, then this is going to be f hat of minus xi means this is going to give you f of x, because minus xi change of variable will give you minus 2 pi I j would be to e to the power 2 pi I j x. So, this essentially says that actually f is also on 2. Therefore, the Fourier transform from Schwarz space to Schwarz space is a bijection. Okay, so far so good. So, now the next important thing which we would like to discuss is the Plan-Searle theorem. So, now what should be the Plan-Searle theorem? So, like just recall, for series, for Fourier series, okay. So, what we know that one, if you are doing with the one periodic function, then this is f of x square dx, this is equal to summation over n varies over z mod of f hat of n square. And that we have got from the inversion theorem. So, naturally we would like to get the inversion, but what should be our statement for the Plan-Searle theorem? Naturally, if f is in Schwarz space, we will denote f square is to be equal to one by 2. So, the most expected Plan-Searle theorem should be, so we expect norm of f hat, and that is what we are going to prove. Thank you.